Hi students, welcome to a new video series. In this video series, we are going to discuss about an important concept in signals and system, that is the sampling theorem. The sampling theorem has so many applications in the entire communication technology and signal processing. Understanding this concept is very essential for understanding the subjects in the upcoming semesters. So before going to start talking about sampling theorem, let us learn something about this horse in motion experiment. There was a scientist in 1800, his name is Edward Maybridge, and he had conducted so many experiments by taking photographs of moving animals. Actually, he was a photographer and he has taken so many different frames of moving animals, and then he has tried to move these images in a cabinet, and when we look through the hole in that cabinet, we can feel like the horse is moving. So we can say that that is the starting of motion picture or videography. Actually, when we see a video or a movie or a motion picture, what we are seeing is that some images or frames moving in front of our eyes. When the images are moving so fast, we are unable to identify them as images. Instead, we get the feeling of continuous motion and we feel it as a video or a movie. So we are also going to conduct the same experiment here in this particular PowerPoint. In this PowerPoint, I have included some different pictures of the horse. So these pictures are taken from the motion of a horse. These are simple pictures and there is no videograph in this PowerPoint, and these pictures are arranged in such a way that it will give the feeling of the continuous motion of the horse. So I am going to demonstrate that using these pictures I will be able to get a feeling that the horse is running. That is what I am going to demonstrate now. I am going to move these slides very fast so you can observe that the horse is running. So that was the basic idea of a 70 mm cinematography. In 70 mm cinematography, in all the theaters there will be a projector room. So this is the projector room, and in the projector room you can see that a wheel is running, and on this wheel there are film rolls, and these film rolls contains so many pictures of a particular scene, and when these pictures or images are moving in front of eyes very faster, we will get the feeling of a movie. That's how we have watched movies in theater in olden days. So this is an example of a film used in 70 mm cinematography, and nowadays this analog technology using film and projector is replaced by digital projectors, and nowadays they are using the digital cinematography technique, but still the concept of frames are there, right? So we are watching movies in theaters or in our computer or mobile phone through frames. When so many frames are moving very fast in front of our eyes, we feel like a continuous movement. When we see an actual scene in front of our eyes through our naked eyes, we are getting infinite number of frames in our eyes. But in cinematography and videography, we cannot store that many images into our computer or into our film. So what technology we are using is that we are trying to fool our eyes by taking samples of a particular scene. If something is happening in front of our eyes, we will take continuous photographs of that particular scene with a small interval of time, and when we move them faster in front of our eyes, we will get the feeling of the motion, or we are trying to fool our eye and brain using these frames to recreate the videograph. This is another example. We are all familiar with this FPS. What is by FPS? FPS is frames per second. Frames per second. So whenever we shoot some movies, using our digital cameras or our mobile phone, it will ask how many frames per second is required. So this FPS essentially means that how many photographs have to be taken in 1 second. So if it is 24 FPS, then we will take 24 photographs of a particular scene in 1 second. If it is 60 FPS, we are taking 60 photographs or images of a scene using our camera. But for 60 FPS, the storage will be very high because it requires more memory to store 60 frames which are taken in 1 second. On the other hand, for 24 FPS the storage is less, but the 60 FPS will give like a lifelike motion, and this 24 FPS will give us a movie-like motion. Because of this reason, modern video games are using this 60 FPS. Okay, video games are using 60 FPS, and the films or movies which we watch in theaters or in our television or mobile phone is using the 24 frames per second. So my point is that instead of recording the infinite number of scenes which is really happening in front of our eyes, we can fool our eyes through some samples of that scenes, right? Simply by taking only 24 samples from the scene, we can fool our eye to create a continuous motion or 60 frames per second, right? Anyway, we are not taking infinite number of images, we are taking only samples of the images, and when these samples are moving in front of our eyes very fast, we will get the feeling of a movie. So all this is possible because of a concept called persistence of vision by Isaac Newton. So Isaac Newton conducted an experiment using his color wheel. So this is known as the color wheel experiment, and in color wheel experiment he has painted some Webster colors on this wheel, and he observed that when he moved this wheel very fast, the color appears white. And he concluded that this is because of persistence of vision. So what is my persistence of vision? Persistence of vision says that any image which moves in front of our eyes will remain in our eyes for 1/16th of a second, right? Now within that 1/16th of the second, if you are able to show the second frame, then you will get a continuous motion feeling, because the first image is still remaining in our eyes or in our brain, and within that time we are showing the second image, third image, fourth image, like that. So because of the persistence of vision, which you have already studied in biology, images which are moving very fast in front of our eyes will give us a feeling of a movie. Another example is DPI. What is DPI? That is dots per inch. So have you heard about this word? Actually, this word dots per inch we use in printing. Actually, whenever we print something on the paper, actually we are creating small dots. We are recreating the scene using smaller dots. So if you zoom this particular portion in this image, you can see these dots. We are creating different dots, and through that dots we are trying to recreate the image. Actual scene of this picture contain infinite number of dots, but we don't need that many dots. You can see there are white dots in between. We are simply putting only the samples on the paper. We can use 96 dot per inch, 300 dot per inch, or 600 dot per inch, right? So using these dots we are trying to fool our eye and brain. So no need to take infinite number of dots, only some finite number of dots are enough to fool our eye, and so these are samples from an infinite number of dots. This particular slide shows the quality of printing when we go with different DPI. For example, this is 300 DPI. See how clear the picture in printing is. This is 200 DPI, 100 DPI, and 50 DPI. So we need to spend only very less ink when we reduce the DPI, but the quality of the printing will be reduced. This concept says that we can perceive an image as an image even if we are using some samples dots of the image for printing. The same is applicable in the case of screen resolution also. Actually, if we zoom into our screen, we can see that the screen is made up of different pixels. These pixels can be considered as samples of a particular scene. Actually we are trying to show only samples of a scene which contain infinite number of pixels. Actual scenes in front of our eyes contain infinite number of pixels, but we cannot represent that many pixels in a computer. It will increase the memory, power, cost, everything. Instead of that, we are using something like 1920 into 1080 pixels for HD screen. This many pixels for HD screen, and we are trying to fool our eye and brain to give feeling of a continuous picture. So again we are taking the samples. These are samples of the actual scene. And one more example is exit poll result. For example, whenever election comes, the news channels will come with exit poll results, right? So how the news channels are able to predict the result without knowing the actual count of votes? They are doing a technique called sampling. So what is meant by sampling? They will go to different constituencies and then they will sample. They will take a group of people, so which are samples of that entire constituency, and they will ask them some questions. Through this survey and all, they will come to a conclusion whether the candidate will win or not. These are all examples of sampling which we apply in our real life. So that is a basic idea of sampling theorem also. So let us go into the introduction part of sampling theorem. So sampling theorem states that under certain conditions, so this word is very important, under certain conditions, a continuous time signal, right? A continuous time signal contains infinite number of samples, right? Infinite number of samples, because it is continuous. It is continuously moving like this, right? So it contains infinite number of samples. So under certain condition, a CT signal or a continuous time signal can be completely represented using its samples. In order to represent that particular signal, we need only its sample. So if we know about the samples of that particular continuous time signal, we can faithfully reconstruct these continuous time signal from its samples without any error. So once again, under certain conditions, so this word is very important, okay? It's not always possible. Under certain conditions, a continuous time signal which contain infinite number of samples, because it is continuous analog signal, can be completely represented using its samples and faithfully recovered or reconstructed from its samples without any error, right? So instead of the original signal, we need only some samples from this signal to completely characterize the signal and to recover the signal and to represent the signal. Now what are these conditions? That question remains. What are these conditions? So this is very, very important. Actually that is what the sampling theorem is dealing with. These conditions are very important, and sampling theorem is talking about this condition. Under what condition we are able to reproduce or reconstruct a continuous time signal from its samples? That is the basic idea of sampling theorem. What is the advantage? Why we go through these kind of difficulties of converting a continuous time signal to samples and processing? Why we are doing all these things? Because this sampling process help us to convert our CT signals to DT signals, that is discrete time signals, and we can process these signals using DT systems. Now we have a question, why can't we process through CT systems? Why we are going for a DT system? In discrete time system, we have some advantages like more flexibility, it is inexpensive to implement, it is lightweight, it is programmable, it is reusable, it has more noise immunity compared to the continuous time system, and it is reproducible compared to the continuous time system. So these advantages of DT system make it a better idea to convert our CT signal into DT signal and then process using the DT system. So that is a basic idea here, right? So what we will do is that we will take a continuous time signal like this, then we will convert that into DT signal, that is discrete time signal. So that process of conversion from CT signal to DT signal is known as sampling. So this process is known as sampling, and after sampling we will get the DT signal. So we will process this DT signal using computer or software program. So we can use computers, then software programs or ASIC chips or DSP processor, anything can be used to process the signal, and then after that the process output will be again DT signal, which we need to be converted back to CT signal, because in real life we have only CT signal, right? In real life we have only CT signals, so we have to convert them back to CT signal. So that operation is known as interpolation, and that also we will discuss in this particular video series. So we will convert them back to CT signal. So that is the reason for going from continuous time signal and sampling it and processing in digital domain or discrete time domain and then converting it back to CT signal. Now, what are the conditions? Now, if I have not taken enough number of samples of this horse running images, or if my sampling is not perfect, right? If my sampling is not in order, or if my sampling does not contain enough number of images, then you will not get the feeling of the horse running. For example, now in this particular slide I have not taken enough number of samples of the horse running images, so when I move this slide faster, you can see that you are not getting the actual feeling of the horse running. Instead you will get a jerking feeling when the horse is moving. Okay, so watch this. So this is because I have not followed the condition for sampling. So sampling theorem comes with a condition that the signal sampling rate must be high enough to permit the reconstruction. So what is my sampling rate? For example, if I have a signal like this is a continuous time signal I have. So this is a continuous time signal. I have to take enough number of samples from this particular continuous time signal. I have to take enough number of samples, then only I will be able to faithfully reconstruct or recover the continuous time signal from this discrete time signal. If I am not taking enough number of samples, then I will not be able to reconstruct the signal. For example, if I have taken these many samples, then I will be able to reconstruct. But what if I am taking only 3-4 samples? For example, one sample from here, another sample from here, right? Only 2 samples. Will I be able to represent the actual signal using these 2 samples alone? No, it's not possible, because there are not enough number of samples to reconstruct the original signal. So that is the condition of sampling theorem. What is that? The signal sampling rate must be high enough to permit the reconstruction, right? So sampling theorem says that we can reconstruct the continuous time signal from its samples, but there are some conditions. Only if we follow the condition we will be able to reconstruct them back. So the history of sampling theorem is very interesting. Actually, before the advancement in signals and system or digital signal processing, the concept of sampling theorem was known to mathematicians like Cauchy in 1841 itself, and there are so many other mathematicians like Borel, Whittaker, and these people also were known about this sampling theorem, and they have independently rediscovered this concept. In 1920s, these 3 famous scientists, that is Carson twins, Nyquist and Hartley, have independently rediscovered the concept of sampling theorem, and it was known in the academic literature. But in 1949, the famous American scientist, and he is known as the father of information theory, Claude Shannon, is the person who made this sampling theorem very famous. In 1949, in his paper, the sampling theorem appears, and he has also cited this gentleman Whittaker in his paper, and from there the sampling theorem became very famous, and the people working in communication engineering started to use the sampling theorem as a fundamental theorem of communication. And that's how the sampling theorem has developed. It has so many applications in communication technology, digital signal processing, image processing, etc. So we are going to watch more about the sampling theorem, its mathematics and its proof in the upcoming video series. Thank you very much for your patient listening.